Okay, so hi again, everyone. Today's event will be about face detection and the easy way. We will tackle it the easiest way possible. We will not go through the mathematics. We probably will have events that we will dive deeper, but for now, we're just gonna see the intuition behind face detection. Um, my name is Negar. I'm the founder and CTO at Elaratech, which is an AI-based startup or small business, if you will, in Georgia, Tbilisi. I'm a machine learning engineer with a focus on NLP, natural language processing. I'm also a chapter leader in Code Academy. Before, it used to be local to Georgia, the country, but then we changed into like a virtual chapter, so we can reach more people from the world, which I think worked. So that's great. Okay, so today we'll be looking at what Viola-Jones algorithm is, and then talk about horror-like features, ADA boost, cascading, and at the end we're just gonna talk about where this event series is going, because I think as far as I think I wrote it in the description that this will be a series of 4 events that will focus on actually creating a face detector algorithm with a good semi-good accuracy. It's gonna be as good as it takes. As it gets, basically. Okay, so and FYI, this event will be totally just me going through the presentation. There's not gonna be any coding involved. So I don't know if that's good or bad news, but yeah. So, Viola-Jones were 2 really cool professors who actually put on the foundation for face detection in deep learning. And let's just go through of how it actually works, because this is the algorithm. Even though it's quite old, they developed it in 2001, we still use it almost everywhere. So let's see how it actually works. So we have this random guy, and this picture, as you can see, this person is very centered. His face is very centered, and he's exactly looking at the camera. And this is actually the best case scenario when dealing with the Viola-Jones algorithm. And of course, in real life, that's not going to happen very often, but just for the sake of the algorithm, we're taking this photo. So the first thing that happens is that we convert the photo into a grayscale instead of having color. And the reason to that is basically it's just very easier to deal with a picture that is 2-dimensional. So backstory, so photos, images in general, if they have color, they will have a 3-dimensional matrix. And it's gonna just take so much more effort and computation power to deal with a 3-dimensional matrix rather than 2-dimensional. And it doesn't really affect the accuracy. So we just, convert it into a grayscale. And then we will have this window, a sub window, or square, whatever they want to call it, and it will just move through the photo or the image, and then it will just try to figure out if it's an actual face. So a face, well, simplest way possible is 2 eyes, 2 eyebrows, and pair of lips, right? And a nose. So this algorithm basically looks for these. Of course, there's more features to what a face is, but these are the most prominent ones. For example, the hairline, or how the cheeks are, and so on and so forth. We have more features, but we're just gonna focus on these, the prominent features. So here, the first sub window, we can see that there's an eyebrow. So cool, we have 1 eyebrow, but then we don't have eyes, nose, or lips. So the algorithm will know, okay, so this is not a face, so it will move down. Now we have 1 eye and 1 eyebrow. It will detect it, but then again, we don't have the other one, so it will know that it's not a face. We keep moving. Now we have 2 eyes and 2 eyebrows, and Well, depending on how accurate our algorithm is, it could detect this as a nose, but still we don't have the we don't have the lips, so it will know that it's not a face, and it will move and it will move. Here we have everything but the lips, so it's pretty close, but then still not again, so it will move again. And here, it finally reaches here, and then you can see that, okay, so we have all the prominent features in the sub window. So it will turn green and say, hey, like, I think that's a face. And it will move again. Still here, you can see all the prominent features. So it will turn green again. It will keep moving. It will keep moving. And, it doesn't see a face anymore, so it doesn't turn green. So this is like very simplified version of what actually happens in the algorithm. So the window, the size of it can be different, usually is different. We iterate through it a lot. The steps that we take, so like from here to here, this is a pretty like large step. In real life, it doesn't work that way, unfortunately. So it's not very, it varies a lot. So, and we have the power to control it, obviously, like how many times we iterate through it, the step size, whether we're going like from the top to the bottom or bottom to the top, left to right or right to left, or I don't know, both of them. So, yeah, so just FYI, but like this is basically how it works. And obviously, I think I said it, but again, the size of the window actually usually is pretty small. So we will iterate through the small and big because like maybe the person is far from the camera. So that's why we would have smaller windows in case. Okay, so that's about it about the algorithm. Now let's talk about Haar-like features. What are they? So this scientist called Alfred Haar came up with something called Haar wavelet. With, if you're familiar, it's sort of like Fourier transform formula. It's basically a repetitive, like it's iterations of squares. It's pretty complicated actually, so I'm not going to go through the formula, not that I understand it, but in general. So just know that the guys from before used this Haar wavelet to come up with a couple of patterns that they found to be very effective to see like what features are like considered as a face. We have edge features, we have line features, and 4 rectangle features. So, as an example, again, this guy, JD, take him as an example. So let's look for, like edge features maybe. So we have it on the nose, if you think about it, because this part is darker than the other side. And yeah, so this is a pattern, right? So yeah, so we just put it there. What else is there? So we have the eyes, because like we have darker and then white. So that's the eye. And we have eyebrows and the forehead, which like this is, darker than the forehead, hence this pattern. Now you might be like, okay, so how do we actually calculate that? Because there's not going to be a person sitting there just being like, oh, like I think that is like darker than the other one. So how do we manage to do that? And the answer to that is basically pixelating the image. So take this for example, and we're just focusing on the nose right now. And as we said, like we think that this part is dark and this part is lighter. And of course, we're not like robots or anything. We're humans, and we're not going to be like it's not going to be exactly white and black. It's going to be in the grayscale, but we're not going to be too picky. We're pixelating this nose. Actually, of course, pixelating is like the pixels are way smaller than this, but just for the sake of this example, take this, and we see here like numbers from 0 to 1, 0 being white, 1 being like black. And as I said, it's going to be in the grayscale between 0 and 1. Yeah, as you can see, so these are like 0.1, 0.2 to 0.3. And this column is what we consider as white. and this one is from zero point 0.4 to zero point 0.8, and which are like, darker. But then again, like it could be, I mean, maybe the contrast is not that much, right? So that's not going to be a feature in case the contrast is not that much. That's why we actually average the left side and the right side, and then we reach zero point 0.1 and zero point 0.5. And what usually is done is that you like take the black and the white and then you subtract it from each other and you get a number. Now, this is like, you can, like, based on your data set, the accuracy or whatever, it changes of what is considered as an actual feature. But usually above zero point 0.3 is considered an actual feature because the contrast is, I mean, basically it's, plausible for us to consider it as a feature. And here we have it as zero point 0.4. So technically, it is actually considered as a feature, which it actually is because it's a nose. So yeah, this is basically how we managed to get what features. I mean, what are the features? Okay, but then it's pretty hard for an algorithm to actually notice what features are important, right? So, I mean, obviously, the eyebrows, the eyes, and the nose, and the lips, and everything are important, as we know. But then the algorithm, how would it know? You know? So that's why we have classifiers that we actually train our model and like with data that we already know, like these are the eyes, these are the nose, these are the lips, and we feed it data and say, hey, like we're looking for these in case that we want to see what the face is, right? So we train the classifiers basically with as much data as we have. But still, I wish it was that easy, but it's not. That's why we have AdaBoost or adaptive boosting. We know about hard-like features and the VJ algorithm. So now what? We train our classifiers. Is that enough? And the answer to that is no. There's something called AdaBoost, which is created to increase the efficiency of binary classifiers. It basically uses an iterative approach to learn from the mistakes of weak classifiers and turn them into strong ones. Okay, so what does that actually mean? So, I mean, in the part that I was talking about the VJ algorithm, it seemed a little bit redundant, most of the steps, because, like, if I know there's no eye, then that's probably not a face. So why am I still calculating the probability that something is an eye or something is whatever, like lips or something? So yeah, so that's why we avoid doing that, obviously, because that takes a lot of time. So we have something called strong classifier, and basically you just sum up how sure the classifiers are that each feature exists. We sum them up, and then we actually figure out if this is a face or not. Because if you think about it, maybe in the picture, the nose is not like, maybe the lighting is somehow in a way that you can't really tell if there's a nose, like there exists a nose, but then everything else is there. So what happens? Like, just because the nose is not very visible, does it mean it's not a face? Absolutely not. But maybe like the nose has lower accuracy because of how the lighting is. Hence why we turn weak classifiers this way when we're, looking at the picture as a whole with all the features and putting it into a strong classifier. So that's basically the idea of AdaBoost. There's a very strong mathematical background on this. Maybe we'll go through it in the next event. But it actually, AdaBoost was technically for the decision trees, but it has been using it. We use it in a lot of algorithms, except decision trees. Yeah. So far, do you have any questions?
I do.
Yeah.
On the part of the numbers, where it has like the black and white.
Yeah, yeah, yeah. Yeah.
Yeah, so I was thinking how do you get that number based on how soft or dark the color is, or how do you get those numbers?
Oh, that's a very good question. Thank you for asking it. So, actually, like when you're using OpenCV, which is the module that we're gonna use, it will turn the image, like each part of it, as a matrix of a two-dimensional matrix because it has only gray and white. And so it technically you would know exactly what it is because of the matrix that we have. And based on that, we pixelate it and you extract these numbers from that matrix. Does that answer your
Okay.
question?
So if the number is closer to zero, it would mean it's like a lighter gray.
Yeah, 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 exactly. So zero, like 0.0 is white, like literally white, and
Mhm.
one is absolutely black. Yeah,
Oh, okay.
yeah.
Thank you, Nigar.
Yeah, you're welcome. Alrighty. So so far we know how the algorithm works when you're trying to see if an image is a face or not. We know ADA boost and we know hair-like features. But still, if you think about it, this will take a lot of time to compute, like a lot of time. And I mean, in programming, everything is about, efficiency. Obviously, we don't want to sit there and wait for our model to, go on for like 24 hours for something that could be done way less because it's very repetitive. So that's why we have something called cascading, which basically is okay, so in each sub window, I mean, the squares that we were talking about, if the first feature, which is the most important feature, does not exist, then we just reject the sub window. Because obviously, if there's no eye in the sub window, then probably that's not a face. I mean, obviously, it's going to be more complicated than that because some people don't have two eyes, or maybe they don't have eyebrows, or whatever. But I mean, that's another thing we're talking about. Aside from identifying imageable features, algorithms also take the relative positions of the features. Yes, they do. Yes, they do. But we usually do it in like when we're doing GANs, so a part of like deep learning as a whole, and not in OpenCV. But yeah, like Apple, the face detector thing, absolutely it does. Yeah. I mean, obviously it's relative, but it does. Anyway, so as I was saying, this saves us so much computing power because if the first one and the second one don't exist, then probably, it's not a face. And we also check the second part and so on and so forth. And you can choose what the window is. For example, you can say, if the fifth feature does not exist, then reject the sub window. I mean, that's on us because we depends on the data set, depends on how accurate we want the model to be, and etc. etc. Now let's take this as an example. Okay, so these are the features that we have, and we're starting with this sub window. Okay, so this is our sub window. We're trying to see how cascading actually works. So the first feature is this. Let's see if we see it here. We actually do. The eyebrow and the forehead, it actually, is this pattern, so it exists. We go to the second one. The second one is this, and we see it in the eye, like white, white, and black. So this one exists as well. We go to the third one, and the third one is this. Well, I mean, this was meant for the lips, but the algorithm could think that the space between the eyes and the eyebrow and the forehead could be something like this, maybe with lower accuracy. For example, it could be like 55% sure, but still it's more than 50%, so we probably would accept it. So the third one is correct, like it exists. So we go to the fourth one, which is this. Now this we do not have in this sub window, which is supposed to be the nose. I mean, maybe with a very low accuracy, like, I mean, maybe like, I don't know, like 20% or 30%, it would take it for here, but then it probably would fail. So we would not even move on to this one. And we would just reject the sub window because, like, these five were probably the most important to us. Does that make sense? I hope it does. Okay. So these are okay, great. So these were the algorithms that we need to understand how OpenCV, which is the library that we're going to focus on in the next event, works, because we're going to be adjusting all of these things that we just discussed. So, sorry, people are joining. That's why I keep pausing. Okay, so what will we focus on in the next event? First of all, we're going to install and code with OpenCV. And then we're gonna do a project which is creating a happiness detector algorithm. But before moving on, I just want to show you what OpenCV is, because I think I've mentioned it a lot. It basically is a computer vision library, and computer vision, in case you don't know, is basically dealing with images in machine learning and deep learning. So that's what we call computer vision, and it's actually a very like huge and accurate library. And as you can see, we can detect and recognize faces, is what we're trying to do now. We can identify objects, which is what we're going to do in the third event. Classify human actions in a video, which is really cool. Track machine learning algorithm, track camera movements and so on. Even 3D models, where we can't really use our computers. We need to like connect to a GPU or something because it's very heavy. Yeah, so that's why we're gonna explore OpenCV. The beauty of it is, even though you have a lot to modify, like a lot of mathematical stuff that you can change in the formulas and stuff, it's still very easy to use, because like you don't have to technically change all of the parameters, right? So it's pretty easy to use even for beginners. So yeah, that's why we're gonna go with OpenCV. And it's worth mentioning that in the like event 3 and 4, we're gonna like create more advanced, the actual deep learning models. So yeah, that's why what you need for the next event is having Jupyter Notebook installed. In case like you've been away from programming for a while, just review what loops, functions, and dictionaries are in Python, like the syntax. And we're gonna talk about regression decision trees and random forests very briefly next session. But I mean, it would be really nice if you actually like, review what the logic is behind them. Because I mean, I feel like every single model is basically them, but like elevated. So yeah, that's about it. And in case you're new, I usually keep my events 30 to 40 minutes long, because I mean, honestly, I wouldn't say more if there was more, like in case I was trying to learn something. So that's why I always keep it very short. So yeah, that was it.